Even in the past with the ancient Greeks, it was pretty obvious that light, white light that you would see, was made up of a whole range of different colors. So if you had this white light that was in front of you, you could say, for example, put a prism in there, and the refraction would cause that light to divide up into different colors. Or similarly, you could just put a filter in front of there, something that blocks out all the other colors of light. And even though you have white light coming in, depending on the filter that you're using, you can have a different color of light that shows up on the other side. And for the longest time, that was kind of the idea, that light was, this white light which covered the entire color spectrum, and you could go from the R of Roy to the V of Biv, and that was everything that light was. But there were some pretty interesting experiments that came about after that time period that really opened up the spectrum and allowed us to talk about light in a lot of different ways. In 1800, a guy named Wilhelm Herschel did a really interesting experiment where he had white light come in through a prism and get broken up into the color spectrum, and then he took a thermometer and measured what the temperature was on the left-hand side of that spectrum, across the spectrum, and on the right-hand side. And so if I click play right here, we can see that this thermometer is on the left of violet, and it's got a temperature of about 68 degrees Fahrenheit. But as I move it in closer, nothing, 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 hits that violet, and suddenly there is a temperature difference. And as I move to the right-hand side, it increases more and more and more and more and more. And then once it leaves the right-hand side, it still continues to go up, even though this is outside of that red band, which would have been very, very frustrating for Wilhelm Herschel at the time. And then once you go past that, it starts to go back down. But there seems to be some place just past red that has something there that's causing the temperature to go up, even though, as far as everybody knew at that point, light was red to violet and nothing else. And so this gap that was just past red, Wilhelm Herschel called infrared. And so now our spectrum was violet to infrared. The following year, there was a guy named Johann Ritter, so that's this fellow right here. He did some work with the same kind of experiment that Wilhelm Herschel did. He had a prism that divided light into violet all the way to now infrared, as they knew. And he thought about symmetry and how, well, if there's something past red, there probably should be something past violet as well. And so after placing some silver chloride just past violet, he saw that that turned a different color. It turned like this darker brown color compared to what it was before. And the only way silver chloride had done that prior was when it was exposed to light. And so that means there must still be more light past violet that you can't see, and so we dubbed that ultraviolet. So at this point in the story, you've got infrared, visible light, and ultraviolet, and that was the whole spectrum of light that you could talk about. Which brings us to the 1860s with James Clerk Maxwell, who by 21, his thesis was to write down 4 formulas, Maxwell's equations, which described all of electricity and all of magnetism. And as part of those formulas that he put together, he found that if you were to take some charge and just give it a little bump, like so, then the field is going to change to send out this wave. And if the electric field is changing, that means there has to be a magnetic field that is created as well. And both of those changing electric fields and magnetic fields are going to travel out looking sort of like a wave. And that wave that oscillates out goes at exactly the speed of light. So if you were to oscillate these charges, the resulting wave really just is light. And furthermore, from these equations, not only do we have light that travels out, that light could have any frequency that we want, even beyond that band of visible light, infrared, and ultraviolet. So now the hunt was on to try to figure out what's actually past infrared and what's actually past ultraviolet. And there were many experiments that were done to figure out what those other types of light would be. Which brings us to the next character in our story, Heinrich Hertz, right here with his Wikipedia page, and he was the first person to experimentally prove Maxwell's equations. And he did it because the people that he was working under, Gustav Kirchhoff and Hermann von Helmholtz, they both said that there was no way that you could experimentally prove Maxwell's equations, that they were just sort of this mathematical trick, and you had to take them for that and not much more. And Hertz said, no, if these equations hold true, then they should have some kind of experimental basis. And so he did exactly that. He proved Maxwell's equations by finding the band beyond infrared, which he called radio waves, but in reality was microwaves and radio waves. Everything past infrared. But for me, the most interesting part about this whole thing, if we scroll down through this Wikipedia page, is that when he was asked about his radio wave experiments and what you could do with them, he said that they were of no use whatsoever, that they were just an experiment to prove that Maxwell was right, that there are these mysterious electromagnetic waves that we can't see with the naked eye, but they're there. And when somebody said, well, what can you actually do with them? What can you actually do with radio waves and microwaves? He said nothing. Whereas now we know that radio waves and microwaves, they're like necessary for everyday life. They're probably two of the most important things that we have each day. So absolutely fascinating story with Heinrich Hertz. And now our band is expanded again. Now we have ultraviolet, visible light, infrared, microwaves, and radio waves. And that takes up our whole electromagnetic spectrum for now. Next stop on our tour through the electromagnetic spectrum was with this fellow right here, Wilhelm Roentgen. And he was the one that discovered X-rays and did, of course, by testing them out on his wife's hand, which is where we get this picture on the left. And he found them by looking at things beyond ultraviolet. He wanted to find things with a larger frequency than our ultraviolet rays on the opposite side of the spectrum to where Heinrich Hertz was looking. So in 1896, we had this discovery of X-rays, which was another piece to the puzzle. And it ended up getting this guy a Nobel Prize. And even though he did try this out on his wife, which is probably not the brightest idea, and it certainly wasn't the nicest one with what we know about X-rays now, he didn't take patents on anything and donated all of his Nobel Prize winning, so he, I guess, wasn't entirely awful. And then the last piece of the puzzle was with Paul Villard, French chemist and physicist. He was looking at radiation, and we already knew about alpha particles, we already knew about beta particles, but what he found was that there was a third type of ray, other than the alpha and the beta, that traveled through and penetrated farther than either alpha or beta did. He didn't really put a name to it. He didn't know what to call it. It was actually Rutherford that later on called them gamma to keep with the same naming system. But then we had our full picture. We had everything from gamma rays to X-rays to ultraviolet to visible light to infrared to microwaves to radio waves, and that entire thing was the electromagnetic spectrum. And so this is our electromagnetic spectrum. You've got gamma rays on one end, which have really small wavelengths, and from our wave equation, V equals F lambda, if the wavelength is really small, that means the frequency has to be really high because all of these waves travel at the speed of light. That's what Maxwell's equations told us, that all of these are light and they all travel at the speed of light. So gamma rays here have really low wavelengths and high frequencies, and as you march to the left, you go through X-rays, then ultraviolet, then your visible light, then infrared, then microwaves, and then radio waves at the very end, where radio waves have a much larger wavelength. We're talking about the difference between 1,000 meters peak to peak for our radio waves to 10 to the negative 12 meters peak to peak for our gamma rays. And the only stuff that we can see is this narrow band called visible light, just this section right here. Everything to its left is invisible, and everything to the right is invisible. But all of these make up the entire electromagnetic spectrum. And that's really the end of the story. Except, Paul Villard's experiment was with radiation, where we had alpha particles coming out, and beta particles coming out, and then gamma waves coming out. It was a bizarre finding that you had these waves coming with other particles. And around this same time period, there was some discussion about this already. And in fact, if you go all the way back to Newton, Newton had a rival named Huygens, and the two of them had been arguing about this idea all the way back then. Even in Newton's times, which is hundreds of years before where we are now, there was discussion on whether light was really a wave or if it was actually a particle. And you're going to have to tune into our video on Thursday to find out what we end up deciding. See you on Thursday.